Okay, this is a video on how to convert between the explicit equation of a function and function notation for a function. We'll look at the completed example first and try to pick out the patterns, and then we will apply those patterns to write the function notation from two explicit equations and then from a description of an equation. So to start, we have an explicit equation, y equals -3 times x plus 2 squared minus 8. And you can see from this that there are two main parts. There's the transformations that are applied, and there's a parent function. And taking those two parts out and breaking them up is how you construct function notation. So we'll start by trying to identify the parent function. Right away you may see that the squared acting directly on the x indicates to you that this might be a quadratic function, and your ability to pick out the parent function becomes pretty important when trying to construct function notation. So this one is quadratic. The way to tell is to look at x in the equation and to see what's acting on x. So x right now is contained in this bracket that's squared. The pieces that act directly on x are the parent function, k, the horizontal stretch or compression, and d, the horizontal shift left or right. If you ignore the compression and the shift, the other piece that's there tells you the parent function. So in this case, we have +2, which tells you that d is -2, and we have a 1 in front of x, so that means k is 1. The pieces that are acting on x are k of 1 and d of -2, and the other piece right here is your squared. That squared should indicate the parent function. So stripping away k and d would leave us just with x squared, and that is our parent function. F of x, our parent function, is x squared. So the first part of function notation is identifying that parent function and writing f of x equals the parent function x squared. The second part to function notation is writing the transformations. And we need to pick out a, k, c, and d from our explicit equation and then write a function equation using those a, k, c's, and d's. So we have a -3 here in front of our parent function that's been transformed. A is -3, and we have a -7 on the end, sorry, -8 on the end, and the -8 represents c in this case. So what we have is an a, k, c, and d. We can use a, k, c, and d to write the second part of our function notation, which is the transformation equation. Transformation equation always starts with y equals, and then instead of a bracket and squared, we strip off the parent function and we just replace it with f. And inside the function, we would place our k of 1 and our d of -2. And acting on the function f of x, we have our a, -3, and our c, of -8. Okay, so taking each piece off and reconstructing it as a two-part equation is how you transfer from explicit to function. So let's try an example. We have y equals 1/2 times the square root of 3x plus 1. The first part is identify the parent function. We'll call our parent function, well, we already used f of x, so let's use g of x for a different function. G of x would equal the parent function. So let's look at what's acting directly on x. On x, we have 3, and that 3 is also being square rooted. So we have the square root of 3x. Acting directly on x in front of it is this 3, which, because it's multiplying by x, indicates that that's the k value. So we have a k of 3. And then that square root sign should indicate to you that the parent function is the square root of x. Inside the square root of x, we have our k of 3, and we don't have a shift left or right because that +1 is outside the square root sign. If it was under the square root, then this would be our, well, part of our d value, once we common factor the 3 out. But since it's not there, this 3 is k, and the d value would be 0. There would be no shift left or right. Plus 1 on the end, since it's outside the function, is c, and the half in front is a. So to construct the second part of our function, we start with y equals, and our function is g, so y equals g, and in front we would put our a, inside the function we put our k and d, and outside the function we would put our c. So a is a half, k is 3, we have our x, d is 0, so we don't have anything else inside the bracket, and c is plus 1, so outside the bracket we have our plus 1. All of these function notation equations follow the transformation equation, and the transformation equation is always structured like y equals a times f, and then inside the function we can have a k, an x minus d, and a plus c. And we're always structuring the second part of our function notation like this, and the first part is pulling out the parent function. I'm going to leave this example for you to try on your own. We're going to move on to the last example. Once we finish this last example, try this second example here by pulling out the parent function and looking for the transformations. Once you've done that, go check with the solution to make sure you got it right. And if you're not sure after that, we can clarify tomorrow in class. From a description, we don't have an explicit equation, so you can do this one of two ways. You can start by writing an explicit equation, or you can try to go directly to the function notation, which is what we'll try to do. So it gives you the parent function right away. However, it does say y equals, so we're going to replace that with function notation. So we'll maybe say we got f, g, h, let's go with k. K of x, and it says the parent function is the square root function again. And now we're going to try to write our transformation equation, y equals. And we can write our transformation equation by trying to pick out the transformations and structure our transformation equation. So we know it should look like y equals, can't see that, let's scroll down, a times, we're using k this time, k, ooh, that's going to be confusing because k is actually a horizontal compression and also the name of a function. Maybe we should use a different letter. We'll stick with it. X minus d plus c. So let's see if we can pick out our letters. Reflection across the x-axis. If we're reflecting across the x-axis would be the horizontal axis. So if we had a point and we were reflecting it, it would go down here, so it would be reflecting vertically. So that means that this is telling you that a is negative. Vertical stretch by a factor of 4, that's about a as well. So now we can conclude that a is 4, but since a is negative, a must be negative 4. Horizontal compression by a factor of 1/3. Horizontal compression by a factor of 1/3, that actually should say horizontal compression by a factor of 3, because we're always talking about our factors as whole numbers. A horizontal compression by a factor of 3 would mean that k is 3. And a translation right 1 unit, shift left right is d, and 1 unit would be 1 to the right. So we're going to replace our k, d, c, and a with the numbers we took out of here. If it didn't give you any information, you'll assume it's 0, so that means that c is 0. And we can write our transformation equation. Minus 4, k is 3, x minus 1, and there is our function notation. If you wanted to expand the 3 and make it 3x minus 3, that would also be an acceptable answer for your transformation equation. If you want to leave it structured like this, that's okay too. All right, thank you for watching, and I'll see you next time.